Hello everybody, happy Thursday. Before we get started on this pretest tutorial video, I want to remind you guys, make sure that you're understanding how to do the problem. It's really important that you understand the process and not really what the final answer is. So make sure that you can replicate these type of problems tomorrow for your actual test. Okay, let's do it together. Problem 1. Sandy is riding her moped through a park. She travels with the velocity shown in this graph. The three segments of the graph are labeled A, B, and C. So part A asks you to construct a motion diagram in the space below that shows Sandy's motion for the entire 8 seconds, so all 3 segments. Before we can even start on a motion diagram, we need to be able to look at this graph and say, what is Sandy's motion doing? Alright, a lot of you are stuck in the fact that you think all graphs are position graphs. So you look at this and you think she's going a constant positive speed, she stops, and then she goes a constant negative speed. If this was a position graph, that'd be right, but it's not. So, since this is a velocity graph, we have to think about what is her velocity doing? What is her speed doing? She starts at a speed of 0. She starts from rest. As time goes on, her speed increases. She's getting faster and faster and faster for those first 4 seconds. She finally reaches a speed of 12. Once she reaches the speed of 12, for a few seconds, she stays at that speed of 12. She's going at constant speed for a while. And then that last second, she doesn't turn around and go in a negative direction. She just slows down, guys. She goes from a speed of 12 down to a speed of 6. She's slowing down for that last second. So she's speeding up, constant speed, slowing down. That's what you have to show on part A here for that motion diagram. Alright, so let's make that together. So the first thing you need on a motion diagram, not that, you need an axis. So I'm going to draw a flat straight line. On that axis you need to label where your 0 is, and you need to label it with an X for position. You're making a motion diagram, that's 1 point already. So make sure you have that axis. Some people are starting to forget those. Alright. We need dots to show the position. So we're going to say it starts from a position of 0. During this first segment, segment A, we talked about she's speeding up. So to show that on a motion diagram, we start with our dots close together, and as time goes on, our dots are going to get further apart. Okay, for that middle section of the motion, part B, she's not stopped. She's going at constant speed. So to show that, I'm going to make dots that are equally spaced. So this spacing that I gave this last dot, I'm going to try to keep that same distance for my next one, and even again for another one. So in the middle here, those are evenly spaced, showing a constant speed. It's at the very end when she slows down. So at the very end, we're not going back to the left, we're not going in a negative direction, we're just slowing down, so our dots are going to get closer together during this last part. Alright, those aren't in a very straight line, but you get the point. Okay, we have our dots, we need to connect them with arrows. So these velocity arrows that I'm using to connect the dots, I'm going to put in blue. So we have arrows, these should all be straight, it's just I didn't do a very good job at it. So these arrows are going in a positive direction, our velocity was always positive. If you did your dots correctly, you'll see that our arrows are getting longer, they stay the same length, and then they get shorter. Alright, the last thing we need to do are acceleration arrows, something new we added in motion diagrams in this unit. During segment A, Sandy was speeding up. So during that segment A on your motion diagram, our acceleration should be in the same direction as our velocity. That's the rule with acceleration. If something is speeding up, acceleration is the same direction as the velocity. So above our dots during this first segment, I'm making little acceleration arrows that point also in the positive direction. Alright, well now let's look at segment C. Let's skip to the end. During segment C, we said she slowed down. So the rule if something is slowing down is that acceleration is opposite the velocity. So our acceleration arrows in this last part are pointed in the negative direction, the opposite direction of the motion. Okay, now we have the middle here. During the middle, Sandy was going at constant speed. She stayed at a speed of 12 the entire time. Therefore, guys, during that segment, Sandy was not accelerating. She stayed at a constant velocity. So in that middle section, segment B of the motion, we don't need acceleration arrows. She was not accelerating. So you only have acceleration arrows at the beginning and at the end of the motion when the velocity was changing. Great. All right, so the last part to this problem, part C, was to calculate Sandy's acceleration. Okay, this is only for segment C. Keep that in mind. A lot of you are doing this for the entire motion, only for segment C. So if you remember, the easiest way to do this is on a velocity graph, the slope of this line gives you the acceleration. So just finding rise divided by run of that last piece will give you your answer really quickly. A lot of you like to use the guess method and label things, so I'm going to do that with you. Calculating acceleration. Let's think about what givens we can pull from this graph. During segment C, the velocity starts here. It starts at a speed of 12. So velocity initial is 12 for this problem. Velocity final, it slows down to here. So it slows down to a speed of 6 for that segment. Okay, another thing we can think about is how much time it took. Now, it didn't take the entire 8 seconds to slow down at that speed. Segment C started here at a time of 7, and it ended at a time of 8. Segment C only lasted for 1 second. So delta t is just 1 second for that part of the motion. All right, our unknown. What they ask us to find, acceleration. Luckily, we have an equation for that. The one that will probably be most useful for you on the board is the one that includes the VF and the VI. This change in velocity is just VF minus VI. So we can use this equation. We know what all three of those are. So substitute those in. VF is equal to 6, that was the final velocity, minus our initial velocity was 12, divided by our time, which we said was just 1 second. So in solving this, 6 minus 12 gives you a negative answer. It's a negative 6 divided by 1. Anything divided by 1 is just itself, so your final answer for this problem is a negative 6. Now the label for acceleration, think about what we did. We took meters per second and we divided it by another second. So meters per second, or another way we learned to write that is meters per second squared. Make sure you have that labeled. That's a point on these problems. Okay, once again, you could have just found the slope of that segment, or you can use the guess method, write it out. But this is the answer that you should have arrived at.